Okay, today we're learning oscillatory motion and waves. This is chapter 16. We've jumped from chapter 10 to chapter 16, and what we've skipped over is essentially a part of the class that engineers do not take in their freshman year. They take that in a separate course. It includes fluids and materials and thermodynamics and thermostatics, actually, thermal physics, but physicists usually cover those topics in different courses, so they skip physicists and engineers and even other scientists like chemists and everything else. They skip that in that class, so we're going to skip it here since both of you are planning on going into physics or engineering or science or something. So we're going to do oscillatory motions and waves, which happens to be a very important topic. It has 11 sections here, so I'm probably going to do this in a couple of different videos, but oscillations mean to move back and forth between 2 points essentially, and of course oscillations often create what we call waves, which waves are essentially a movement of matter or energy through whatever, through some medium, well, it doesn't necessarily have to move through a medium, but waves are a movement that is caused by an oscillation, a movement through matter or through energy in some way. And so it's a transmission of energy, in other words. And so here's an example of an oscillation. You have some kind of stretchy material here that he's holding, whatever it is, and he pulls it over here to the left, and then he lets it go, and it vibrates back and forth. There's an equilibrium position in the middle that if he lets it go long enough, the energy will eventually dissipate in the form of heat and by air friction and whatever else. And it will eventually return back to this equilibrium position, but while it's vibrating, that equilibrium position is pretty much right in the middle. And the reason that this type of motion occurs is from what we call restoring forces. So forces that are always pointing back towards the equilibrium position. So when he pulls this thing to the left, the stretchiness or the elastic force of the material wants to pull it back towards the equilibrium position. When it bounces back through the equilibrium position and goes to the other side, to the right side, then the force inside the material is trying to pull it back towards the left, towards the equilibrium position. So that restoring force is always pointing towards the equilibrium point, no matter which side the material is on. It's so that the restoring force is a changing force. Not only does it change direction, but it also changes magnitude. And it is usually pretty comparable to Hooke's law force, or the elastic force that we're used to, where you have some constant K, and it's also relevant, or it's also excuse me, directly related to the distance. So the further you pull this material away, the further you displace the object, the more force that it feels going to go back towards the middle. And what this results in is what we call harmonic motion, or a motion that can be mapped using sines and cosines. And this constant that we talk about is what we call the force constant. So things that are more difficult to stretch, more difficult to bend, usually have a stronger force constant. Things that are easier to bend have a weaker force constant or a smaller force constant. We know that this force constant is fairly linear through a certain distance, through certain distances and through certain forces. But eventually, if you stretch a spring too far, it will just bend the spring. So it's not infinitely linear. But here's an example where we're going to actually calculate the force constant for a suspension system in a car, for the springs on the wheels of a car. And we have an equilibrium position we're going to call x equals 0, and that's a good thing to do when you're dealing with oscillations and springs and waves, is to have the equilibrium position be the x equals 0 point. Because then everything on one side can be considered positive, everything on the other side can be considered negative, and we'll have this sort of chosen symmetry to everything. So it'll be nice. In this particular case, we have a car that settles 1.2 centimeters when an 80 kilogram person gets in, and we're going to say that before the person gets in, the x equals 0 will be the equilibrium position. So the springs are already loaded with the weight of the car, but we're going to ignore that for the moment. And it settles down 1.2 centimeters, And the displaced position, which we'll say that going down as the person gets in, will be a negative, so it's negative 1.2 times 10 to the minus 2 meters. And then the force of the person that is exerting, the force that the person exerting on those springs is, of course, their weight, which is their mass times the gravitational constant, 9.8 meters per second squared. So using Hooke's law, which is F equals negative kx, we can solve for k, essentially. So k is equal to negative f over x, and we put in the force, which is their weight, over the negative 1.2. The negative over the negative cancels. You just do this arithmetic, and it's fairly simple. 6.53 times 10 to the 4th newtons per meter for that particular spring on that car. For those springs, technically there would be 4 of them, so you would divide by 4, at least 4. Some cars actually have 2 springs per wheel, but you would usually have at least 1 spring per wheel in a car. So and we've seen this before earlier in the class, where you have the energy for a spring. The potential energy of a spring is 1/2 kx squared. So the k and the x being the same thing as they were in Hooke's law. And that's the potential energy of a spring as you stretch it or you compress it. And that potential energy, of course, can be turned into kinetic energy, can be turned into launch something upward and be turned into gravitational potential energy or whatever else. And so it's just part of the work energy theorem in the end. So here we're going to calculate the stored energy or the potential energy in a spring with a force constant of 50 Newton meters, and will be compressed 1.15 meters. And then we're going to go ahead and see what kind of speed an object will get if it is launched by this spring, if that potential energy is turned into kinetic energy. So here's the picture of it, the spring. It's inside of this little spring gun. And part A is just 1/2 kx squared, and we're going to get 0.563 when we plug in the numbers they give us. Pretty simple stuff. Make sure you convert centimeters to meters and everything else. But then in the second part, we're going to set that elastic potential energy equal to a final kinetic energy of the ball. And then we are going to solve for the velocity. So kinetic energy is 1/2 mv squared, of course, and then the kinetic energy 1/2 kx squared. We go ahead and set them equal, solve for v, we get this equation here, and we plug in our numbers, and we get excuse me, approximately 23.7 meters per second of velocity for that ball. Now, as we start to allow springy things to oscillate, to move back and forth, we're going to find that we're going to have some things we want. Sorry, I'm sitting right underneath the flight path to an airport, so I apologize for that. But anyway, as we study these things that are going to now oscillate, these springy things that are going to go back and forth, we're going to want to measure things like frequency and period, and we've done this before. Remember that frequency is the inverse of period. Frequency is measured in per seconds, what we call hertz, so 1/seconds. So the frequency is the amount of oscillations, or the amount of cycles per second. And period is the number of seconds that it takes for a cycle to pass by, or the time that an entire cycle takes. And so here's just an example of how to use this very simple definition or relationship. We want to find the frequency we've got a medical imaging device, for example, that's producing an ultrasound, and it's oscillating with a period of 0.4 microseconds, and we want to know the frequency. So if you know the period, the frequency is 1 over that, and so you go ahead and you just take 1 over the period here, and make sure that you have it in seconds, and then you get a frequency of 2.5 times 10 to the 6 hertz, or 2.5 megahertz, right? And then in part B, we have the frequency of middle C is 264 hertz, and we want to know what is the period, how much time does it take for one complete oscillation. So frequency is 1 over period, so you solve for period and you get period equals 1 over frequency, and then you go ahead and put 1 over 264 hertz, and then you get 3.79 times 10 to the minus 3, or 3.79 milliseconds for one wave of the middle C note to do its thing. Okay, so now that we understand frequency and period, we can get into a little bit of the actual motion. We're going to start with what we call simple harmonic motion, a very basic type of movement. And of course, it's called simple because it is very basic. Harmonic because we will model it using the sine or the cosine function, very simple function. So we're going to have a spring here, a very special spring that has a very linear k constant. It's going to be very very perfect spring. We're going to put a mass on the end of it, and this mass will be on a frictionless table, of course. There'll be no air friction or any friction of any kind, no heat loss in the spring or anything. Perfect system. And this equilibrium point here we'll call x equals 0. And then we're going to displace this mass, pull it over here to the right to give it some displacement of x. And then we'll release it. And as we pull this spring over to the right, it's going to feel that Hooke's law force to the left, and it's going to want to be accelerated to the left. And so when we actually release it, it will be accelerated to the left, and as it goes through the center point or the equilibrium point, it will be going as fast as it can go, because once it gets past that, the spring will start pushing on it. And so the Hooke's law force will actually be to the right, and it will actually slow the mass down. And then as it completely compresses, it'll stop the mass, and then it will accelerate it back to the right towards the equilibrium position again. So you can see here that the restoring force is always towards the equilibrium point. And this will just continue on and on and on. If this is a completely perfect and frictionless system, it will continue forever, but of course that never happens. So it will eventually stop in real life. It turns out that we can actually calculate the period of a simple harmonic oscillator, and we've done it before in this class with gravity. And we did it also with this particular system, the horizontal sliding mass system. So we're just going to show you that again, if you don't remember. The period is 2 pi times the square root of the mass over the spring constant. And the frequency, of course, would be 1 over that, which is 1 over 2 pi square root of the spring constant over mass. And neither of these depends on how far you pull the spring. As long as you don't pull the spring so much that it bends it or that it's not behaving linearly anymore. If you pull it further, it'll be moving faster as it goes to the middle point, and it will go through its entire motion in the same amount of time, or using in the same frequency and the same period. So here we're going to calculate the frequency and period of some bad shock absorbers in a car. If you, of course, don't have shock absorbers are devices that prevent the car from bouncing up and down when it hits something because it's on springs. So if you don't have those and you jump on the bumper or something, the car will bounce up and down, and it will bounce up and down with a particular frequency with a particular period, and that will be pretty close to this frequency calculation here, 1 over 2 pi to the square root of the spring constant over m. And so if we know the spring constant, you know the mass of the car, you can actually calculate this, and they give those things, so we can just plug them in, and we get a frequency of 1.36 hertz, which means it would bounce up and down once every 1 1/3 second or so. Which, if you've ever done that to a kind of medium-sized car, you know that's about true. My brother had a friend that had a car with terrible shock absorbers, and when he jumped on his hood, it was about, I'd say, once every 1.5 2 seconds, so it's pretty close. And then if you want to calculate the period of that, oh, this one has actually a little bit less than a second, but anyway, if you calculate the period 1 over the frequency, then it's 0.738 hertz. So we're in the same range about. The interesting thing about this is that you can actually map this out in time as well. If you have a mass on a spring and you hang it and you start it oscillating up and down, and then you put a little pin on it or something that will draw on some paper that's rolling by, you will actually be able to see that this does map out as a cosine or a sine depending on where you start it. You get this nice harmonic curve here, and then you can start to realize what's going on. You can also do this theoretically, you can do it mathematically and everything else to show that this is true. It's a little bit beyond this class, but that's okay. Anyway, we're going to go ahead and start with using the cosine as the function that describes the motion, describes the position or x of the x position of our mass. We'll use x for up and down or side to side for the horizontal oscillator. And as a function of time, so as time goes by, where is our oscillator? Is it right in the middle at the equilibrium point? Is it far to the left? Is it somewhere in between? So what we're going to do is we're going to let big X equal our maximum distance away from the equilibrium point, and then that will be called our amplitude. Big X will be our amplitude, which is the maximum distance or the maximum displacement that the mass has from the equilibrium point. And then we'll multiply by cosine 2 pi times the time that has passed over the period. So the period is something that is a constant number all the time. That's the amount of time it takes for one wave to pass. And everything else in there is a constant 2 in the pi, except for the little t, which is the time that has actually passed. And it turns out through some calculus we can actually calculate the velocity as well of this object. It turns out to be negative the maximum velocity times the sine of 2 pi time over the period. So we've got some equations here that will give us some information. We also have an equation for the acceleration. For the acceleration, it ends up being negative the spring constant times the magnitude divided by the mass times the cosine of 2 pi times the time over the period. And so a lot of stuff coming out of that one. And that'll tell us how much the mass is accelerating. The interesting thing about these is that you have the negatives, of course, on the velocity and the acceleration. And then also another interesting thing is that these things can equal 0. The velocity can equal 0, the position can equal 0, the acceleration can equal 0, depending on what you choose for your time. At certain times, the position is 0. It's right in the middle. And that's not the same time as the velocity is 0, it turns out, because the cosine and the sine don't go to 0 at the same time. They don't go to 0 with the same numbers inside of them. So when the cosine is has a 0 over here, so if t equals 0, in other words little t equals 0, and the cosine of 0 is 1, so that would mean that x would be equal to x. But when the sine of 0, if this thing is 0 over here for time 0, when the sine of 0 is 0, so at t equals 0 in this case, this thing is entirely 0. So its velocity is 0 at time equals 0. So it's kind of interesting. And that should make sense to us because of the motion of an oscillator. So let's take a look at the motion of an oscillator. Here's our oscillator. We lift it up all the way to the top of its motion, and right before we let it go, its velocity is 0, but it has this displacement that is maximum x. We've displaced it upward to a maximum value. So it has maximum displacement of x. Its x's displacement is x. Its velocity is 0, and you can see that on the graph here. The velocity is 0. And then its acceleration will be a maximum as soon as I let it go. As soon as I let it go, it's going to accelerate, and it's going to have its maximum acceleration because the spring is pushing on it as hard as it can when you lift it up here. As it pushes on it, the spring expands and it pushes less and less and less, and then it starts to pull the other way. So its acceleration will get less and less and less, and its velocity will get more and more and more, and its position will go closer and closer to 0. So as it gets to 0, which is this point right here, it has a 0 position. It's right in the middle, which is what we called 0, but its velocity is at the maximum velocity. And then its acceleration is actually turning around to go the other direction. So, and you can see that here at the beginning you have a maximum displacement. This is maximum x, and it has 0 velocity, and it has a negative acceleration. The acceleration is pushing away. And then when it goes through the 0 point, which is right here where x equals 0, remember this, the horizontal axis is time, and the x-axis is, or the vertical axis is the x-axis in this case. So when x equals 0, the velocity is at its maximum right here, and the acceleration is at 0. It's not accelerating at all when it's right through the middle. When it's at the other end, when it's down here fully stretched, it stops again. So it's fully stretched, it's at this point, the fully maximum negative position right here, and it's stopped again. The velocity is 0 again, and the acceleration is actually positive. It's upward. The acceleration, the spring is trying to push the ball upward at a maximum strength. So the force is at a maximum and the acceleration is at a maximum. So those are the interesting features of the harmonic motion. Simple harmonic motion. So the mass on the spring, good example of simple harmonic motion. The simple pendulum, also uh, a decent candidate for simple harmonic motion, as long as you don't, as long as you have a long string compared to the distance that you're going to swing it back and forth. If this length L here is much longer than the length of the path that it's going to swing back and forth, then it works really well. Um, and this is what we call a simple pendulum. It just has a string here that has very little or no mass, and all of its mass, all the mass of the pendulum is concentrated at the end here. And you get this free body diagram where you have this tension force that is upward here, and this mass, the weight of gravity pulling down here, and they combine, these two forces add together to give you a force that is a restoring force this way. This force which pushes it back towards the center of its motion, which is right here. And we can do all the math for this. We've done it once before, and you get the same results as before. And the results are that the period is completely independent of the mass. It doesn't matter how much mass is on there. It just matters how long it is. So here's the calculation for the period of a simple pendulum: 2 pi times the square root of the length of the pendulum over a gravitational constant g, little g. And we can actually do a lot of things like that. For example, we can measure the gravitational constant g using this pendulum. If we know the exact length of our pendulum, and we can calculate what the period should be, and then we calculate the period actually is, and then we can get what g is measured to be. So they measure here g to be 9.8281 when they measure the period and measure the length and then calculate g. So it's a good instrument for calculating what the gravitational constant is. And here is an engineer building two simple pendulums, and the pendulum hovers 2 centimeters above the floor, has a bob with 10 kilograms, another one has a bob of 100 kilograms. We want to describe how the motion of the pendulum will differ if the bobs are both displaced by 12 degrees. They both have the same length, right? If they both have the same length, then they're not going to change at all, because it only depends on length. So the energy of the simple harmonic oscillator is very similar to the energy of the spring. You have the kind of energy that can be stored in the simple harmonic oscillator is 1/2 kx squared. That's how much energy can be stored in the spring. But then, of course, a simple harmonic oscillator also has kinetic energy at different points, and it changes back and forth. And if you do this for a pendulum, you're going to end up with rotational stuff. So pendulums, it's 1/2 ml squared omega squared, 1/2 mgl theta squared, and those are your kinetic and your potential energies there, and those things have to be constant as well. Where L for a simple harmonic oscillator is just the mass times the r squared, or mass times the length of the pendulum squared. So that's where the ml squared comes in there. That's not what the L is. Sorry, that's what the I is. So this is ml squared here, and then there's an for the I squared. But anyway, because remember that we replace, well, anyway, there's a mass replaced with is replaced with I's and everything else with rotational things. But they just write it out for us, makes it a little easier. This is also our K's in there and everything else. But anyway, point being is it's not all that hard to figure out. But then you can start to calculate maximum velocities, for example. In this case, they calculate the maximum velocity of a simple harmonic oscillator to be the square root of k over m, the spring constant over m, times x. And that's for, of course, a spring. If you have a mass on a spring, if you have a mass on a string in a pendulum, then you can do the same thing for the maximum omega, or the maximum angular velocity, and get the square root of the gravitational constant over the length times the maximum angle. So you can actually calculate the maximum speed of these oscillating systems, and that's exactly what they do in this example. They just plug in the numbers that are given and calculate those maximum speeds. Once you calculate that maximum speed, you can actually create the equation for that oscillator, because the equation for that oscillator is equal to that maximum speed times, it's actually negative that maximum speed times the sine of the of the 2 pi times the time over the period, which we saw before. So here they're doing that equation. Well, they're doing a similar thing to those equations. So, all right. So I'm gonna hold it there and move on to the next half of the chapter in a little bit, so that I can. I need to plug in my computer for one thing, but also I want to do some homework examples and other things. So I'm going to start with section 6 next time, and we'll go through section 11, and we'll go from there next time.